Welcome to a video lecture on electric fields. This will follow along in sections 18.6 and 18.7 of your textbook. Let's get going. A field in general is the space around one object in which a force is exerted on a second object. It's kind of the general idea. We've already talked about gravitational fields with the idea from a universal law of gravitation, where there is some force on an object with mass due to other objects with mass. And around that object there exists this area of a gravitational field where if you put another object with mass, that will feel a force. And what we're going to look at now is the electric field. And we'll also look at the magnetic field in a little while. I think the magnetic field is kind of one of the more easier ones or more common ones that you're more familiar with. Let me just put it that way. Of looking at. The electric field is the area around a charge in which another charge will feel a force. So it's the alteration of that space around the charge where some other charge will feel that force. Now, we generally are concerned, we use test charges, which are generally positive, and they always have a very small magnitude in order to determine the field the force at that point. So, and the reason for that is otherwise they will alter the position or location of the original charges. We have the formula here. It says that the electric field depends on the force at that point divided by the test charge. Q naught is the test charge. And so if we're looking at this, it becomes that the force, which depends on charge 1 and charge 2, and the charge is charge 2 is Q naught, or the test charge. It just becomes that the electric field is equal to the electric field constant, the electric force constant, K, times charge 1 divided by the distance between the point that we're concerned with and that charge squared. So we're kind of looking at that simple idea there, because the second charge will cancel out. Here's what I was just referring to from the idea that electric field depends only really on some point charge and the distance between that and where we're looking, along with the constant. So, and this is for just the electric field created by point charge. The other idea that we're going to look at is an electric field created by a parallel plate capacitor, but we'll get back to that in a second. So here, the electric field at one point, it's due to the force exerted on by the charge on some small test charge. So what we're really concerned with is just really the distance and the magnitude of that original charge. Now, multiple electric fields will add together like vectors. So here we have the same idea, thinking back to the electric forces. Have they added together like vectors? So here we have the charge from the electric field from A plus the electric field from B combined to equal some net electric field following along with trigonometry and vectors right there. The second type of electric field that we're going to be concerned with is a parallel plate capacitor. Now, a parallel plate involves, obviously, two parallel plates set up across some distance where there is some charge on each plate. There's a charge per area. And the other idea here is that you have some medium or something in there that allows or permits a electric field to become created. And it's really that permittivity of whatever the material is in there that we're concerned with. And the permittivity of free space, this is that constant epsilon naught, is this constant for within our universe here that we've measured to be how much the medium around of just in a vacuum will allow an electric field to set up and transmit and to act on other objects. So we have a parallel plate, which is, as I just mentioned, two plates apart from each other, where there's some distance, and the electric field in there doesn't really depend on the distance apart, but it only depends on the charge and the area across the two, and the area of the two plates. Electric field lines are drawn to show the electric field at that point based on the charges around there. And they always go away from positive charges and toward negative charges. And the strength or the relative magnitude of the electric field depends on how many electric field lines are packed in close together or how close they are. So as you get close to a charge, the electric field has a greater magnitude, and you will see, like on, for example, a point charge, the electric fields diverge away and they're very close near that center point. And as you get farther and farther away, the electric field weakens and therefore becomes the lines are much more spread out. So electric field lines away from positive charges towards negative charges, and they exist, and they really just go on forever. But as you go on forever and out to infinity or whatever, the field drops towards zero, and the magnitude of the field lines becomes so far apart that we're not concerned with that. So here are some examples of some electric fields. So we have on our right, let's start on the left and go to the right. We have a positive charge, and you can see the electric field lines diverging away from that point charge right there. So this is the idea of a point charge, and the lines are tightly packed close to it near that point charge, and they diverge away. So as they move away, the electric field itself gets weaker. Next, in the middle, we have a negative charge where the field lines are converging on that negative charge there. They're getting stronger as you get closer. And all the way to the right, we have a parallel plate capacitor. And if you notice here that in the middle, and we're going to look at the middle kind of section there, that the field strength is the same throughout the middle. Now, the only place where the field differs is at the ends of a parallel plate, the edges of a parallel plate, where it kind of wraps out into or kind of bulges out into that extra free space there. But through the middle of a parallel plate capacitor, the field strength is always going to be the same, and it doesn't depend on how far apart the two plates are from each other. So that's all that we're really concerned with. Here are some more examples of some electric field lines. Here we have the two positive charges on the left, and you can see both of the field lines are wrapping away from each other. They're repelled by the opposite charge, and they're going away from there. So you can kind of see how the curve is set up there. And on the right, we have a positive and a negative charge, and you can see how they combine along, how the field lines combine there. The force felt, or the force felt, by a test charge is always tangent at any one point to that line. So if it's curved or something like that, the force is going to be tangent to that curve there. And you can see how as you move away from kind of that axis line further to, this is for the right picture of the positive and negative charges, you move further away from the axis right between the two charges, up and down, the field lines start spreading out. And those mean that the force at that point is start getting weaker and weaker and weaker. The force that a charge would feel right there would be weaker and weaker and weaker. Now, keep in mind, this is always, the field lines are based on a positive test charge. So you go away from a positive charge and towards a negative charge. All right, two quick review questions. One, an isolated point charge of having a strength of 15 microcoulombs is in a vacuum, and at a distance of 0.2 meters to the right, a positive test charge of positive 0.1 microcoulombs is used to determine the strength of the electric field. What is the strength of the electric field? Look back on that formula of how you would find first. You can calculate the force between the two charges, and then based on the strength of the test charge, you can find and calculate the electric field. Second, I would like you to write down any characteristics that you think are important for electric field lines. So how are they directed? How do they indicate field strength? How do you know positive and negative, et cetera, et cetera? So anything that is important to kind of think about for an electric field line, kind of come up with a list of maybe 4 or 5, probably 6 important or key points about electric field lines. Thank you very much. Make sure to answer the questions online, and have a good night. We'll see you tomorrow. Bring questions, because this is a difficult topic. Bring questions with you to class, and we will go over them and discuss them then. All right? Thank you very much. Again, good night.